Goedemiddag. Good afternoon. I can see you're all sleepy, so it's a good time after lunch actually, because we're actually going to give you a little bit of entertainment, and we're talking about smart potatoes. In fact, let me call it a smart spud. So I'm going to take you on this journey, but I first want you to see how we can be innovative. So we can talk about smart farming with smart sensors, and I'm going to co-present this with my co-worker, Dr. Andre Broekman. So very importantly, why do we have to innovate? So I know I saw this beautiful potato, and it's buffalo, and I pinched it from one of the display tables. It's really gorgeous, beautiful. And not all your potatoes look like this. So often you do have some damage, and that's mainly bruising, damage from dropping. And yes, I know people often do not consider a potato. They think it's a rock, and you can drop it. No, you can't. And you can't drop it because every piece of damage will actually cause an opening for a pathogen to infect. And I always say to the students, just imagine the environment. Just think of the air. It's just full of fungal spores and everything floating around. And all these microbes want to do is attach, infect, invade, and rot it. Not all of them. There's some good guys and we've just seen the biocontrol presentation. And just so, by the way, about the biocontrol, we have the South African Biocontrol Manufacturers Organization, where we actually take you on a journey to help you get your product registered. So by the way, do become a member of SABO. So let me take you further on this journey. And as a plant pathologist, and I'm proudly a plant pathologist, and we live in this world of rotten potatoes, rotten fruit and vegetables, and our main task is to prevent that. So it's really about extending your shelf life, ensuring quality, and most importantly, making sure the customer is happy. So we do have a few problem areas in the industry. Yes, and I do know harvesting is another challenge, a challenge on their own, and you do get a lot of damage happening. How much? How can you adapt your practices to reduce damage? And then secondly, yes, during the loading and the packing and the transport, you do have more damage happening. Once again, how can you reduce it? And then once this potato arrives in your pack house, well, it's got another journey ahead. It's got to go through that whole pack line, vibration, movement, bumping. And then once you put it into a bag, then the bag gets handled. So ultimately, we decided, let's engage with the potato industry and then develop a smart spud for the industry. Now this smart spud, the whole idea is to follow the journey from the soil to the plate. And if we can use this technology and ensure that it's available to farmers so that they can improve their production system. So we've got data loggers in here, and we can now monitor several parameters that we've selected. We can make this real time, and can we, at the end of the day, extend your shelf life? So, with any good project, you need a good team. Let me introduce your team. We're talking about transdisciplinary research. Yes, there's the first two engineers, and there's the two plant pathologists. So I decided, well, let me ask the engineers to come and tell you more, not only about our smart spud, but about our smart avo, smart tomato that we've already developed. And with that, Andre, can you come and tell them about our smart spud?
And
here's your spud.
There we go, the important part. Good afternoon, ladies and gentlemen. Thanks for the opportunity that we can speak with you. By day, I am indeed a civil engineer, but by night, we actually do also design and build smart potatoes. This one is not smart enough to sing you the I Want to Be a Simba Chippy song quite yet, but it does feature some interesting characteristics that paints us an interesting picture. So the origin of this is actually in a railway engineering project, which is more my background, and we designed what we call Clippy. And I'm going to show you a photo of what that looks like. So Clippy is a smart rock, and as civil engineers, we actually want to know what does rocks do in a railway formation, and it's difficult to instrument it. So how do you know the history or the life of that rock? So instead of instrumenting it, we made a smart rock an instrument in and of itself. So with the wonders of 3D printing, you can create an external protective shell, and inside of it you put electronics, battery communications, and importantly sensors. And these are the same that you find in your cell phone when you turn them in a landscape mode and the screen rotates. It's the same low-cost technology that's included in this clippy device, and it's waterproof and robust enough to survive a very harsh environment. Ultimately, we thought, can we not adapt this for agricultural applications? And it turns out that you can. So we collaborated with the SAGA, or South African Avocado Growers Association, to build what we called SMAVO. We engineers not very original with the name, so the Smart Avocado. The first 3 prototypes weren't all that waterproof, but we did see the potential back in 2019, just before COVID. Then we went on a very large sampling campaign. We improved a few things on the hardware side, and we endeavored on one of the largest sampling initiatives, I think, in the country that has been completed to date. 3 provinces, 24 pack houses, and more than 12 million data points that was collected. This was during COVID, so a few logistical challenges, but the learnings from that we can also apply to the industry. So what did we learn about the avocados? That's also a highly sensitive fruit in how you handle it. It's very sensitive to bruising, so what did we see? From the data gathered, acceleration and rotation, so again, acceleration in terms of bumping, if you let it fall, that's what we register. We devised the means to understand what does a good pack house look like. So from the 24 pack houses, you will see that's the distribution of forces on the surface of, if this was the avocado, an average pack house and one that we call not optimized or a bad pack house. And this essentially involved a lot of handling. They handled the avocados very rough, they let them fall, and we could characterize this with our instrumentation. When we look at the statistics of this, I'll keep it very simple. The less you let your avocado fall in terms of total freefall distance, and the less you handle it and bump it around in the environment, this is what is visualized. So the less you bump it and the less you let it fall, that's a good thing. And the opposite is, of course, a bad thing. But you can see there's a spread or distribution, so we can effectively benchmark different pack houses against one another to understand what is the typical characteristics of a good pack house. How should we design it? What can we learn from that environment and deploy it across the whole industry to get better quality produce? We went as far as programming these smart avos. We put them on a container ship down in Cape Town. We had a satellite photo of the actual ship on which they were loaded, and that headed to Amsterdam, and about 15 days later they were offloaded in the port of Rotterdam. And we could actually see the barometric impacts in terms of the atmospheric conditions of the reefer container and even the movement of the ship. So from the farm to the truck, down to the handling facilities, onto a ship all the way to the Netherlands, we can understand what the story of that avocado had to tell us. And that's where we collected them on the other side of the world, and we showcased this is a viable technology. Similar situation for the smart tomato, that's more the local market, and again with Prof. Korsten we did some investigations there, and also deduced some correlations between tomatoes that goes bad and then the impact that smart tomato felt. Same electronics, same principle. But excessive vibrations leads to lengthy cell damage and ultimately a shorter shelf life. And very interestingly, the correlation, I'm a railway transportation engineer, at the Kranskop Toll Plaza, those rumble strips, we definitely picked that up in the fruit. So quite significant damage that we also need to talk to the engineers. Finally, while we're here today to talk about the Spuddy, the same electronics are on the inside of the Spuddy. We can just develop a different shell. We added some metal and lead weights inside just to give it a bit more density compared to an avocado and tomato. Put them through a pack house close to a farm in Bobsfontein, and this is what we saw. So what you're seeing is a history of the accelerations. It looks a bit like a cardiogram. And we go through the process of first installing it in the pack house, and then, or the processing line, travels through the washing drum, inside the washing drum, dryer conveyor, and the sorting conveyor. And the higher these peaks that you see, the higher the G-force or the acceleration of the Spuddy that was experienced. So we can conclude from the washing drum, it had its most violent sort of experience, then the drying conveyor, and then the sorting conveyor in terms of amplitude, and we can see exactly how long that was in that process for. We can also detect what's called free fall. So when it falls like that, we can measure the distance at various points along that process, the highest of which was 300 millimeters for this one. And again, also visualize on the surface of that spud or potato where those forces will actually impact it. On a longer duration, we also looked at harvesting them, getting them out of the soil, and you'll see there's significant acceleration. So the highest impact occurs during that phase. then it goes onto the tipper on to the packing warehouse, and then onto the conveyor similar to what you just saw. So it's the entire transportation chain that we can investigate, and it tells us an interesting story of that. Even if it's just one single spuddy, we can gain a lot of insight into that. And again, free fall distances metrics we can also see there. For the most part of the journey, the potato was on a singular position. I can deduce that from all the little dots that concentrated there. Here and there it moved about, but for the most part it rested on a singular spot during that transportation journey, where most of the contact surface was for that. So we can also see historical data. This was from the SMAVOs, and it looks very identical. So we can use historical research that we've done to date, compare that to things like what we've done with the potatoes to augment our understanding of the fresh produce transportation chain from start to end. So in conclusion, the sensor platform that we've developed to date for agricultural purposes can be adapted for the potato industry. We're seeing very good correspondence between different data sets for different projects that we've used to date, improving our understanding of that, and also identifying where do we see the highest acceleration and resulting damage to the potatoes along the packing lines. It was particular for that washing drum section. So Prof, I'll hand over to you to conclude.
Thank you very much, Andre. And I just want to say we're continuing with this project and we're expanding it and also including packaging material and developing that technology further. So from the team, thank you very much, and funding for support, thank you very much for that, making science work for you.